my YouTube channel. In this video, I'm going to continue with my previous subject discussion, and we have stopped at the types of wave, transverse wave and longitudinal wave. This part is the last part, is the third part for this chapter, where we'll talk about reflection, refraction and diffraction, and also the phenomenon, how to make use of diffraction. You may want to refer to my Form 4 Chapter 5 on the details of reflection and diffraction, reflection and refraction, because for wave, they behave like the same behavior. So, to start off with, the first phenomenon they call refraction, FL, reflect. What happened? They have the incident angle and also the reflection angle, just like what we had in Form 4 Chapter 5, light, where in Form 4 Chapter 5 for light, we treat light as particle. Now actually, light could be treated as wave in this manner. They call dualism of light, because light also could be reflected as well as being refracted. And the same goes with the sound wave. So wave could be also could have reflection and also refraction, and light could also be regarded as wave, light wave. Yeah, because previously in Form 4, I discussed light in the terms of particle, just like a ball bounce around. At the same time here, light also behave like a wave. You may treat light as also wave because they have reflection and also refraction in some objective question especially. So, what is reflection in terms of wave? Whether light wave, sound wave, they behave the same in terms of reflection. Say you have hard surface, not necessary to be a mirror, but for light you need to be a mirror, shining surface, okay? On this case, we put it into mirror, flat surface, mirror, so that light or sound wave could behave like a wave. Okay, you will see the behavior, right? So, mirror, and this is a virtual line called normal line, because any angle measure from incident is always from the normal line. So, you have incoming wave. This is the wave front. What happened? It will be reflected. So this is the wave front, and one way to distinguish it is the incident. Maybe the incoming, the direction incoming. This is called incident angle. I should be the same as with the refracted angle. Okay, refraction angle, same, right? So the angle of I, same as with angle of R. They're supposed to be the same. Okay, angle of incidence, angle of reflection. Just in case, okay, I hope you have gone through my Form 4 chapters. Incidence, and this is the reflection. If you haven't, then I hope this word will help you out with it. So the condition would be like 0, I less than 90. Okay, so there's no way that the incident angle could be 90, because 90 will be flat here already, coming from here. So there's no way to do that. So when it's 0, something interesting here is I want to highlight what happened is it were to be equal to 0. When the incident equal is 0, means it's echo. You get echo. It's incoming, outgoing. You bounce at the same angle, because angle always measure from normal. Okay, it's not measured from the surface, angle from the normal line. Then what are the characteristics? Based on the diagram, what are the characteristics? 1. Okay, the incident line, the incident wave, and incident wave normal line and also the reflected wave, they are the same side, they are the same plane. Plane is a surface, okay? They're all the same surface, it's in the same area from cross-sectional view, okay? And previously we learned velocity, wavelength, and frequency, right? So what happened? The wavelength after reflected, the velocity, and also the frequency, they are all the same after reflection. Ideally, yeah, there's no loss of energy. Frequency, to be particular, frequency depends on the source. Unless you change the source frequency, then the reflected wave will have changed. Otherwise, the frequency is supposed to be the same. Frequency is the same. Yeah? The only thing changes is the direction. Okay? Because obviously the direction changes. The direction of wave changes. Obviously it's changed, right? Because initially it's from here down, then bounce off. That's why the direction changed. The rest is the same, yeah, for reflection. Then next, we would have refraction. Okay. Okay. Refraction, like in Form 4, Chapter 5, refraction is the measurement of how the light wave bend towards the normal line when it's being slowed down, means it's being slowed down, bend towards the line is slowed down. The actually same is true for wave. And one way to really look at it, I mean, if you have really, I think you have gone through it by now. If you have watching this video, you have see the how the water, deep water, I mean calm water run deep, right? So this is what it means by that, okay, physically. Now, give an example. Let's say you have a tray, top view of a tray. We have a pool of water. In this tray, you're going to insert an object, a prism, perhaps a prism in this shape. In one of your school experiment, I believe, a glass at the bottom of this tray is a top view, yeah. Then you're going to have a vibrator. I think this vibrator here. What happens when it starts to vibrate? You're able to, you have a photograph, of course. You may have a camera capture the image, isn't it? And then steal it with a stroboscope still, and then you're able to calculate what's the speed of the wave, okay, in your school experiment, obviously. So what happened is, instead of using a wave, yeah, so I'm going to make it parallel, okay. There's some way to make it called diffraction, but there's some way to make it parallel, so that here we have a parallel line incoming. Actual wave is not a straight line, yeah, it's supposed to be curved, but when you pass through some obstacle, then it will become parallel, okay, parallel. Okay, so when it reach, we focus at this side. When it reach the prism, the object, what happened? The wave become closer, meaning the wavelength changes until when it exits okay, So this is basically what you see from the experiment. Okay, so go in there, go in, then it will bend. It will bend accordingly to a normal line. Okay, so this is the experiment actually. Then what happened is, I mean from your books, okay, in terms of side view, then if you look at the side view, what happened is like this. You have, I mean, then this is, and this is an object. Okay, waters here, maybe you have wave. When it comes to here, you become, the ripple will be, you have shorter, you have a short wave. I mean the lambda is smaller here. Okay, and then here the lambda 1, lambda 2. Okay, obviously lambda 1 is greater than lambda 2, right? Then this is your water. Then what happened? That's why they say smooth water runs deep, or calm water runs deep. That's the reason behind it. Then there are some books that explain on why is it so. Because actually when it reached here, what happened? The force, the energy or the force used to push on down to it, the reaction force and reaction force will pull it up, isn't it? So therefore the time here is shorter, and therefore the response time is shorter, and therefore the ripple is more frequent as compared to here. This is a deep region. Okay, the force push onto the shallow water, the response time at the shallow water is shorter, therefore you get a response to the ripple and reduces the wavelength. You doesn't really know much about it, but the one way to really understand this is because it's closer, therefore the ripple is smaller. I mean the wavelength for ripple will be smaller. So what the characteristic is all you need to know to answer the objective question. With here, what happened from here? I mean the observation. Observation first, what changes? The direction changes. What else? The speed, because lambda changes, therefore the speed change. Frequency do not, because frequency depends on the source. And also lastly the wavelength. They all changes. Okay, all of them changes. What do not change? Frequency, remain the same. Okay, before and after, frequency remain the same, because frequency depends on the source. It's constant, right? So you have the speed will have changed from what we have learned earlier. V equals to F lambda. Okay, if frequency is constant for both cases, so therefore your F deep are supposed to be the same as with your F shallow. Okay, your shallow water is supposed to be, the frequency at the shallow water is the same as with the deep water. So what happened from this relationship? Therefore your V deep over lambda dip will be same as with a V swallow over the swallow frequency, right? It's a constant. So therefore, you will see when the lambda at the swallow reduces, therefore the velocity here should have increased, meaning the time for this side of the water appear to have ripple will be faster, and therefore the wavelength will be smaller. Okay, got it? If you don't get it, pause this video, rewind to the previous few minutes to listen to what I have said earlier, because they are constant. Okay, you may have a graph sometimes in a subjective question, says the graph for it would be like, okay, you have velocity versus lambda. So what happened is the gradient. I think the trick for this question is the gradient. The gradient are supposed to be the same. Okay. Why I always get this screen? Oh, okay. I'm sorry, I'm using a Mac system. Whenever I press on something, a new screen pops up. Okay. So because of this, you have a direct proportional line. It is the gradient. You look for the gradient, isn't it? This is the gradient is the frequency. Okay, because frequency depends on the source. Alright, that's the second thing you want to learn. Now the third thing, before we get to third thing, some important rules, not rules, something they need to know. Up till now you learn about wave, sound wave, like water wave, water ripple, and also light wave. Light also behave like wave because light do behave the same as how the sound wave behave. We have refraction and also refraction. So light could be considered as wave. Light, what we see is called the Balmer series, is called the visible light. So the spectrum, okay, they call electromagnetic spectrum. It's something I think it's good for you to know. So we start with okay. Royberg or VI boy, get your own rifle. Okay, we'll start with VI boy. Oh, with a different color maybe. Okay, VI boy, get your own rifle. Okay, VI boy, get your own rifle. What does it stand? It stands for violet, indigo, blue, green, yellow, orange, red. VI boy, get your own rifle. So what does it mean? It means you need to actually at least know if you've gone through physics. So what happened is the visible spectrum, the wavelength for visible spectrum for the eye of yours will be able to distinguish what's their color. So the capability of your eye, as long as the wavelength comes between 400 nanometer to 700 nanometer, your eye will be able to distinguish it. You are able to see it. So most of the thing, like the color you see from the screen, should be in this range, 400 nanometer to 700 nanometers. And then what happened? The one in between green is actually maybe around 550 nanometer. It's actually green. Or green could be many gradient, of course, but around 550 would be green. So sometimes in some objective question they ask you about the wavelength. What wavelength would it be? So it's good to know, first of all, VI boy, get your own rifle. Red is 700 nanometer, green is 400 nanometer, because from left to right, based on this rule, VI boy get rifle, from left to right, what happened? The wavelength increase, right? Increase. So what happened? Anything beyond red, what do you call? Anything beyond red, we call infrared. Anything after red is called infrared, meaning hot. Yeah, your remote control infrared, or maybe infrared from the sun. Okay, even warmer, hot. Anything higher temperature than infrared, you have microwave. Maybe I use another color. Microwave. Microwave, like you use it for your food, where the vibration, okay, the frequency vibration is similar to the frequency of the water. That's why we have resonance, and therefore it heats up. Water heats up, and then you boil your food. That's microwave. And then after microwave, you have radio wave. Radio, maybe another color. Radio wave, where radio wave is something with even longer wavelength. Okay, goes from left to right, it's longer wavelength. When the wavelength gets longer, you become less harmful. Yeah, radio wave is not so harmful. Anything in this visible, those in between here, those are called the visible, you can see, visible spectrum. So what about violet here? Anything lower than violet in terms of wavelength, anything lower than that, they call ultraviolet. Ultraviolet is not good, because ultraviolet will cause, from sunlight, ultraviolet, it will cause skin cancer. It will changes. Actually, your eye, you get cataract in the sunlight. Okay, of course, UV, you have UVA, UVB, UVC. Okay, depends on the wavelength, right? Then lower than that, lower than infrared, you have X-ray. Is even more hazardous. You use X-ray for soft tissue, maybe low dosage. You use it for X-ray purpose. X-ray. Okay. Then even shorter wavelength. You have, says, gamma ray is even more more harmful, because gamma used to kill bacteria. In Malaysia, you have this thing called Sinar Gamma. It's an institute in around Bangi, I guess. Sinar Gamma is used to kill off bacteria, for example. Used to kill bacteria. So, and gamma ray is actually not good for human. We can talk about it. So, towards the left, when the frequency wavelength reduces, it will become more hazardous. Okay, dangerous when the wavelength is low. Likewise, if we don't talk about wavelength, how about we talk about frequency? Now, for frequency, which side have higher frequency? Again, from the equation of, now they are all EM wave is based on the speed of light. They travel at the speed of light. So meaning C. Okay, I've gone through my previous video. What does it mean by C? Okay, so for C equals to F lambda. This is a constant. So far at time, nothing would be able to travel faster than light at this point of time. Okay, we don't know in future. So when your wavelength increases, your frequency reduces, yeah? So meaning from left to right, your frequency reduce. So I'll put it, how can I put it? Reduce from left to right. Okay, from left to right, frequency reduce because of this equation. You doesn't need to memorize it, because if you know the wavelength already, eventually you will know it, because when wavelength increases, your frequency reduces. That's all about it. Okay, so important, you need to know the wavelength for visible spectrum. Then the rest you will be able to jot it down accordingly. I mean, it comes up by itself. Okay, pause my video, reverse to the previous beat, and go through how I get this whole spectrum. Lastly, that's the last phenomenon we talk about. They call diffraction. Now, diffraction, you haven't learned it in Form 4, Chapter 5. This is the first term in Form 5, Chapter 1. Now, if you want to know more about it, more image about it, kindly, since you are now in YouTube, meaning you have internet connection, kindly search for this term and look for image. Search image from internet. How does it look like? You have animation of how does it look like if you didn't get to see it at school. Okay, so what is diffraction? Diffraction is like the phenomenon of wave that spread out. That spread out once it passed through an aperture, meaning a hole. Aperture is a very small hole. Aperture or a small obstacle. Okay, so you may go through some image online, or maybe from school. Maybe you have seen it also, meaning there are some parallel wave, and then purposely they pass through a very tiny opening. What do you get? The shape of the wave will have bend. Okay, and what you see, it's spread out. Okay, initially one direction. So this phenomenon is called diffraction, like a D, diffraction. Okay, in order for it to happen, the size of the opening has to be smaller or comparable to the wavelength. Okay, or at least smaller than the wavelength. So the condition, first, your wavelength, meaning here to here, crest to crest, wavelength, your wavelength has to be greater than the aperture size A. If it's greater than that, it will occur. You may change this size and see how it changes accordingly. I mean, you may get to see from online. Okay, and then observation. Just like the previous two phenomena, observation, the frequency the wavelength and the speed remain the same. Okay, do not change. The frequency do not change, the wavelength do not change, the velocity do not change. What changes? The direction changes, the pattern also changes, of the wavefront changes. Okay, the rest remain the same. Okay, so you may pause this video and then go through my previous few minutes if you have missed any beats. Okay, it's not much of calculation here, it's about the phenomenon. Alright, then what we advise you to do now is before you proceed to the next part, because I have one last part, is pause this video, go through the exercise. For this one, I think I would say is about 8 to 10 short question answer, or perhaps 10 questions of objective questions, or multiple choice relates to refraction, and diffraction. I think it helps you out to better understand what I've gone through. Or you may read through the relevant reference from your reference text. Okay? Because next, how could you use this diffraction? One hole doesn't help much. Next, it will be called superposition. Okay? Okay? A new term is not the fourth phenomenon. I think I would say is superposition. Meaning, what happens if now you have two of this wave? You have two holes, what happens? They will overlap. What is superposition? Superposition meaning is a combination. Combination of wave. Two waves come together. Combination of wave, how? Okay? That takes the sum of the amplitude. Okay, say for example, scenario, okay, you have one here, another one here, come together, then they will overlap, isn't it? Then what will happen? Now, when the crest meets with the crest, you will get double crest. Okay, 2A. From the equilibrium, of course. This is A, of course. Okay? And this is called the constructive interference. When two come together, you have a name called constructive interference. Okay? When two of them are the same, meaning they are called two waves, they are in phase. Some new term, because in some objective question they tend to throw you out with this kind of term. In phase, when they are the crest with the crest, you get constructive. Now, when you have crest meets with trot, those are called, what happened? Same, you get calm water. A note. Okay, a note is none. None is a note. Okay, so this is out of phase. I think this chapter you will have to learn quite a lump sum of new term. Note means nothing. Note. Okay, and this is called disruptive interference. Okay, this is note. When you have constructive, this is called anti-note. not a node lah, meaning because node is none ma. Node is none, then antinode is. Okay, that's all about superposition. For calculation, how do you calculate them? Okay, because what happened, you have two of these in my next page. I'm going to finish in this video, don't worry, where you have double split experiment, Young double split experiment, right? Young double slit experiment. Okay, what it does, you have what? In some case, I will going to draw physical way. I mean, this is okay. One aperture, two aperture, maybe single source, so that the frequency will have the same. So what happened? And then you have, I think you have seen this in your experiment, one of the experiment. This is the screen, white screen, perhaps a white screen. Okay, so it's quite confusing, so I want you to listen carefully of the terminologies. It's all about terminologies. You have one source. I mean, some objective questions, sometimes you draw diagram differently, but most importantly, you have two slit, meaning you have two source, 1, 2, then the wave will be, you know, all the line comes out here, and then superimpose, and then what happened, you see bright light, dark light, bright light, dark light, alternate bright light, dark light. Okay, so this is bright light, or sound light if you have sound, but sound is very hard to see, so you use light, is easier for you to see. Light also behave diffraction. So how normally they will ask you for a few things, where you have lambda equals to ax over d. So what is the a? How are you going to define it? We're going to define this way. A is actually the aperture size. It's actually the distance from here to here. Normally in objective question, they don't draw you this diagram. You need to visualize from the wording, and then you translate it into a diagram, and it helps you to solve question. Trust me, this is the way to work it out. And then x is actually the distance between the bright light. D is the distance between the source, from the source to the screen. Depends on how question want to put it in. Okay, sometimes you will say, oh, the source is how many meter away from the screen, and then you will see the distance between the dark and 3 dark lights is how much, and you need to visualize 1, 2, 3, then you divide it by 2. I mean, it's a very technical thing, yeah. You really need to do it. You need to translate it into a diagram. Then you will be able to calculate what is the wavelength. I can't help much on this because you really need to do those exercises, at least 10 to 15 calculation questions from chapter, I mean from the reference or textbook. At least 15 questions to really get used to this equation, ax over d. A is the distance between the source, x is the distance between the constructive interference. You will have bright, sometimes you measure the bright light, sometimes you measure dark light. It depends on question, doesn't really matter. As long as you measure the distance between the constructive or destructive, you will get the same answer. Doesn't really matter, but you don't measure the constructive and destructive, no. Okay, if you measure the constructive, then constructive, or you measure the destructive with destructive. Sometimes you say, oh, the 1, 2, 3, 4, 5. This distance of 5 bright light is so much. Then you divide by 1, 2, 3, 4. You divide by 4, not 5. 4. Okay. So one last condition for this to occur is it has to have coherent light, coherent source. Not necessarily to be light because it could be sound. What does it mean? Coherent means you have the same frequency, same amplitude, and in phase. They are going to have the same frequency, same amplitude, just in case, and the waveheads are supposed to be in phase, meaning up to up or down down, meaning two source. The best way is to use double slit, then you get from a single source, double slit, then you get in phase. Okay, then only you will have superposition. Right? I think that's all for this chapter from 5 chapter 5. From 5 chapter 1. I like those thumbs up button. I like it a lot. I hope you like my video. If you're first time watching it, kindly press on thumbs up button or subscribe to my channel for more upcoming video. And when you're finished watching it, you may pause it, download it, or share with friends through the link, or at least I hope you read through the reference, or at the same time, in 1 week time, you have finished off at least 20 questions for this video. If you're not aware of, every video should come up with about 15 to 20 questions. Home practice yourself before you proceed to the next video. That's all from me. Thank you.